So I've got Microsoft Basic running on my homemade breadboard computer, and that means I can try out some longer programs. But I found that even if I take a simple program like this and just try to copy and paste it into the terminal program, it gets garbled. And of course, if I try and run this, I get a syntax error. The problem is the computer is taking too long to process each character, and so it's missing some of them. If we look at this garbled mess that we got here when we tried to paste that program in, it actually matches the text we pasted in, but it's skipping lots of characters because it's busy processing one character while several more characters come in, so it's only catching some of the characters. Now I can work around this problem with this terminal program, which lets me configure pacing. So I can have it put in a 20 millisecond delay between characters, and that'll give the computer enough time to process each character that I'm pasting in. So now when I paste that program in, you can see it sort of types it more slowly, and it all makes it in. So I can list the program, there it is, I can run it, and of course it works. But of course I'd like the computer to be able to accept input as quickly as possible without having to artificially slow down the rate that I type or paste it in, and without it ever missing a character. And an effective way to do that is to use interrupts. So when a new character comes in, it'll trigger an interrupt, so the CPU will stop whatever it's doing and read that character. Now conveniently, the UART we're using, the 6551, can generate interrupts. So here's the datasheet for the 6551, and it talks about interrupt logic here, and it says the interrupt logic will cause the IRQ line to go low when conditions are met that require the attention of the microprocessor. What sort of conditions is it talking about? Well, it lists a bunch of different conditions, including receiver data register full. And that's what we want. When a new character comes in, it gets sent over the serial connection 1 bit at a time, and when all of the bits have been received, the receiver data register will be full. And so this chip can generate an interrupt, which we can use to have the microprocessor read that data register and put it in memory right away before another character comes in. And so to enable those interrupts, we need to set this bit 1 here in the command register to 0 to enable the interrupt requests. So if we look at our code, the beginning of WASMON is where the command register is initialized. So right here, we're setting it to 8B. If we flip bit 1 off, that'll make it 8-9, and that'll enable interrupts when we receive a character. So now when this chip receives a complete character from the serial interface, it'll bring pin 26 low. So I'll connect pin 26 here to pin 4 on the 6502 microprocessor so that when that goes low, it'll trigger an interrupt and the microprocessor will stop what it's doing and run our interrupt code. And for now, I'll disconnect the interrupt signal coming from the versatile interface adapter since we're not going to be using that for the moment. And then also this interrupt line from the 6551 is an open drain output, meaning it's going to pull that line low when an interrupt occurs, but otherwise it'll be floating. So to keep it high normally, I'll add a pull-up resistor here. And the value is not that important. I think this is a 1K resistor, but most anything will do. So now when that interrupt happens, let's look at our BIOS code. It's going to jump to whatever address we have here for our IRQ vector. Right now it's just a bogus address, but we can write some code for our interrupt request handler. I'll add a label for the interrupt request handler. And to start with, it'll just return from the interrupt. Then I can set the IRQ vector to point to that label. And so now whenever we receive a character, it'll run whatever code we put up here in our interrupt request handler. So what do we want it to do? Well, we want to take the character that was received and put it in memory somewhere. And it doesn't really matter where as long as we can keep track of it. So we might have a pointer telling us where to write a character to memory, a write pointer. And let's say that pointer is pointing at address 7. So when we receive a character, we can write it to memory at address 7 and increment the write pointer to 8, which is where the next character will go. And then when whatever software is running wants to read a character from the user, rather than reading it directly, it'll use a second pointer that says what address in the buffer to read the next character from. So that's our read pointer. In this case, the read pointer says to read the character from address 7. So the software reads H from memory as the next character typed and increments the read pointer. So now the read pointer and write pointer are equal to each other. In this case, they're both pointing to 8. And so the software can tell there are no more characters that have been typed. But now if the user starts typing really fast and the software isn't ready, each character can be quickly written to memory at the next available spot pointed to by the write pointer. Then whenever the software is able to catch up, it'll grab the next character at the address stored in the read pointer, incrementing it each time to keep track. And so this allows the user's typing to be disconnected from whenever the software is ready for the next character. And this sort of buffer is referred to as a circular buffer because, it's a fixed size, but when the pointers get to the end here, they just wrap around to the beginning. So in this case, if the pointer is a 4-bit value, when it gets to F and we increment it, that 4-bit value will just overflow and it'll wrap back around to 0, 1, and so forth. And then it just keeps going. So as long as the buffer's big enough and the input's not coming in so rapidly that the write pointer overtakes the read pointer, this will work perfectly. So to implement something like that, we'll need to set aside some space in memory. Now we need a read pointer, so I'll reserve 1 byte for that. And we also need a write pointer. And both of these are 1 byte, so each of them can count up to 255, and then when we increment it again, it'll wrap back around to 0. So that'll work perfectly if we make our input buffer 256 bytes long. So for the input buffer, I'll reserve 256 bytes, and 256 is 100 hex. Now we have to think about where in memory we're going to put these variables. So for the 1 byte variables, the 0 page is a good place, since accessing it there is going to be a little bit faster, though I guess space is somewhat limited. Then for the buffer, since it's larger, we'll just put it in its own memory segment. Now for the 0 page, Microsoft Basic is already using the 0 page for a bunch of stuff. If we look at our custom defines that we set up in the last video where we got Basic running, we had to define these ZP start variables to tell it where to put stuff in the 0 page. And I think the easiest way to add 2 more bytes to the 0 page without conflicting with anything here is to add a ZP start 0 at the beginning, starting at address 0. And since we just need room for 2 bytes, the read pointer and write pointer, I'll just nudge the rest of these ZP start addresses by 2. So instead of 0, this will be 2. Instead of A, this will be C. Instead of 60, this will be 62. And instead of 6B, this will be 6D. So that gives us 2 bytes free starting at ZP start 0. So then I can go back to our BIOS file and add an org statement to explicitly put these 2 bytes in that space we just freed up. Then we've got the input buffer, and that's going into its own segment in memory. So we can configure where that goes in the linker config. So I'll add the segment here. So this is the input buffer segment. We'll load it into the input buffer memory location, and it's read-write. Then we need to define the memory location for it. So it'll be the input buffer location, and it'll start at address 0300, which I believe is currently not used for anything else. The size is 0100, or 256 bytes. The type is read-write, and the file is going to be blank since we don't want to write this to the ROM file since it's just going to be in RAM only. Okay, so now we should have memory reserved in a reasonable place for these variables. Now we can use them. So I'm going to define a couple subroutines for working with our circular buffer. So I'll just go down here. And first, to initialize the buffer before we do anything else, we want to make sure the read pointer and write pointer are both pointing to the same place. So we'll put a 0 in the A register and store that to both the read pointer and to the write pointer, and then return from the subroutine. And actually, since this is a circular buffer, it doesn't really matter where we start. There's nothing special about starting both of these pointers at 0. So, we could save a couple bytes by getting rid of this load A, and then loading A with whatever random value happens to be in the read pointer. And that'll still initialize the buffer to be empty since it sets the pointers to be equal to each other. Now I can write a subroutine to write a new character to the buffer. And so when this subroutine gets called, we'll assume the new character is in the A register. So I'll start by loading the current write pointer into the X register, and then we can store the character from the A register into the input buffer at offset X. So if the write pointer happened to be 7, now there's a 7 in the X register, and we're putting our new character into memory at the address of input buffer, which is 0300 plus X, gives us 0307. Then we want to increment the write pointer. So we'll say increment write pointer, and we can return from the subroutine. So that'll write a character to the circular buffer. Next, I'll write a subroutine that'll read the next character out of the circular buffer and return it in the A register. This would be very similar, except now we're putting the read pointer into the X register. Then we can load the A register with whatever's in the input buffer at offset X. So again, if the read pointer is 7, we'll put whatever character is in memory at address 0307 into the A register, and then we'll increment the read pointer. So increment read pointer, and return from the subroutine with the character now in the A register. Now, as we write these subroutines, it's useful to document what registers they modify so we don't get surprised by any side effects of, modifying, for example, the X register unexpectedly. So the init subroutine modifies the processor flags as well as the A register because we're loading the A register with the read pointer and writing that to the write pointer. The write buffer subroutine is modifying the processor flags as well as the X register. And then the read buffer subroutine is modifying the processor flags as well as the A register, because it's returning the value in A, and the X register. Finally, I'll write one more subroutine that computes how many bytes are in the buffer. So that is how many have been written to the buffer but not yet read. So we'll start with the write pointer, and basically we're just going to subtract the read pointer from it. So we'll set the carry bit, and then subtract with carry the read pointer. And setting the carry bit and doing a subtract with carry will basically give us the difference of the write pointer minus the read pointer. And it'll wrap around correctly with our circular buffer. So this ought to just work. That leaves the difference in the A register, so now we can just return from subroutine. And this one just modifies the flags and, of course, the A register. So those are all the subroutines we need for a circular buffer. So now let's start using them. The first one we need to call is init buffer, and we want to call that as soon as the computer is powered on or reset. And of course, whenever that happens, the computer is going to jump to whatever code is pointed to by the reset vector down here. And in our case, that's over in Wasmon. And so here's that reset label. And so this is the code the computer runs as soon as it's reset. And so pretty much right away, we want to jump subroutine to init buffer. And so I'll put that here right before the clear interrupt disable, so that once we do that, any interrupts that come in, the buffer will already be initialized. And so now we can write the interrupt handler to process each incoming character. And basically all we're looking to do here is load the character into the A register, then write that character to the input buffer using the write buffer subroutine. And that's basically it. But we do need to do a couple other things. Since we're modifying the A register with this load A, we need to push it onto the stack before we begin, and then pull it off the stack before returning, because the interrupt handler is expected to leave all of the registers other than flags the way it found them. And then another gotcha is that the write buffer subroutine that we're calling here modifies the X register. And that was sort of this note here, modifies the flags and the X register. So we also need to save the X register and restore it before we return. And then finally, the way the interrupt works is that when a character arrives, the UART is going to pull the interrupt request line low, which causes the processor to pause whatever it's doing and run this interrupt handler. But if we don't acknowledge the interrupt, the UART will just keep that IRQ line low, and as soon as we exit the handler here, it'll immediately run again and we'll be just stuck in an infinite loop, just running this interrupt handler forever. And so we actually have to do something to acknowledge the interrupt. And the way that we do that is simply reading the status register. So just by reading the status register like this into the A register, that's enough to cause the UART to know that we've handled the interrupt, and then it'll bring the IRQ line back high again until the next character arrives. Now in theory, we could check the status register here to confirm that the interrupt actually came from the UART. But since it's the only thing we've got physically connected to the IRQ line, we can just assume that the only thing that can cause interrupts is incoming data. Now, if we did have other things that could cause interrupts, then we would actually have to look at this status and potentially look at other potential causes of interrupts, make sure we're handling an interrupt from the correct place. But for now, this will do as our interrupt handler. And I think if you actually look at how long this interrupt handler will take, if you actually look at how many how many clock cycles each of these instructions takes, as well as the instructions in this write buffer subroutine, it turns out to be around, I think, 60 clock cycles or so, somewhere in that range, which, a 1 megahertz clock like we have is going to take 60 microseconds to handle an interrupt. Whereas at 19.2 kilobits per second with a start bit and a stop bit, it's going to take 520 microseconds to receive each character. So 520 microseconds to receive a character, only 60 microseconds in this interrupt to process it. So even if we're pasting in a block of characters all at once, the computer is only going to spend about 10% of its time in this interrupt handler. And so now we've got input being handled by the interrupt handler here and going into our circular buffer. So now we need to modify the input routine to fetch characters from the input buffer rather than directly from the UART. So here's our character in subroutine. So it started out by checking the status register of the UART, seeing if a new character had arrived, and if not, branching down to no key pressed. Here what we can do is replace this with a call to the buffer size subroutine, which will return the number of unprocessed characters in the buffer. So here, if there are no new characters, this will return a 0 in the A register, and the 0 flag will be set. So in that case, this branch will actually be taken, no key pressed, if there's nothing in the buffer. Otherwise, if there are characters in the buffer to read, it'll drop down here. And now instead of loading data from the UART into the A register, we can just call read buffer, and that'll put the next character from the buffer into the A register. And that's basically it. Except again, we need to be careful because this read buffer subroutine modifies the X register. So we need to acknowledge that we're changing the way this read subroutine works by noting here that it's going to change the X register. But this subroutine is called a lot of places, like from within Microsoft Basic, and that's not really the expectation that Basic has. It makes sense that it's modifying the A register because it's returning the whole point of here is to input a character into the A register. But it doesn't really make sense for this subroutine to modify X. So instead, we'll push X onto the stack here and then make sure we pull it back off the stack before returning. And that should pretty much be it. So as long as everything's using this input routine, the interrupt handler is going to put all new input into the buffer, and this routine will read it out. So now Microsoft Basic is already using this, but Wasmon is still interacting directly with the hardware. So let's change that. So let's switch over to Wasmon and let's find where it's reading characters. And so here's where Wasmon is reading a character directly from the hardware. And this should look somewhat familiar. This is what we were just kind of looking at for reading a new character from the hardware. But we can just get rid of all this and just call our character in subroutine. And that'll read in a new character from the buffer. And if there is no new character that's been typed, then this subroutine is going to return with the carry flag clear. So we can branch if carry clear back to next character to just sit in a loop here and keep calling character in until we get some kind of input. So that actually simplifies this a bit since it doesn't have to interact directly with the hardware anymore. And also since character in already echoes the character back, we can get rid of this line here to echo. And so now everything should be using our new interrupt-driven buffered input routines. So let's give it a try. I'll save everything and get out and run make. And then write the EEPROM image it creates using MiniPro. We're programming a 28C256 EEPROM. We want to unprotect it before we write and then protect it after writing. And we're writing the temp eater.bin file to it. So there it goes. Success. So I'll put that EEPROM back in the computer and reset. And well, that's kind of weird. It's just sort of scrolling off the screen. I reset again here. All right, so if I type 80, whoa, it's like it's repeating each character that I type sort of sporadically. If I hit enter, weird. So I think what's going on is we're getting extra interrupts, and the only thing that can cause interrupts is the UART because it's the only thing that's connected to the interrupt line. But if we look at the UART datasheet, the description here of interrupt logic says that the conditions which can cause an interrupt will set bit 7 and the appropriate bit of bits 3 through 6 in the status register. So bits 5 and 6 correspond to data carrier detect logic and data set ready logic, with bit 3 corresponding to receiver data register full. And so these are the conditions that can cause an interrupt request. We only care about the receiver data register full. So I guess this assumption about the only source of interrupts being incoming data isn't right. Yeah, so maybe we need to actually check this status register to verify that the cause of the interrupt really was incoming data. But really, I didn't expect DCD or DSR to be doing anything at all since we're not currently using them. Those are pins 16 and 17 here. And, well, actually right now they're not connected to anything. So maybe because they're just left floating like this, they're causing spurious interrupts. Let's actually just connect both of them to ground to see if that stops the extra interrupts from happening. There's DCD. And DSR, and that actually seems to have maybe worked. It's stopped it anyway. And it looks like I can type, and yeah, Wasmon seems to be working. So let's run basic. All right, basic seems to be running. So far, so good. Let's try copy pasting that program in again. Oh, well, it's still doing it slowly, but I guess at least it seems to still work. But let's get rid of the pacing here so we can see our buffer do its thing. So I'll clear out the program, nothing there, paste it in, boom, there it is. Nice, much faster. So that's a huge improvement. We can send data as fast as the hardware will allow, and we're guaranteed not to miss anything, unlike before. However, there is still a limitation, which is that the buffer is only 256 bytes. So if we tried pasting a larger block of text, significantly more than 256 bytes at a time, we could overrun the program. So we take this program here, paste that in, In this case, you can see we overran the buffer. That is, the write pointer caught up to the read pointer and lapped it, so we lost data. Now, fortunately, there is still a way to fix that, but that's going to have to wait for the next video.